Welcome to the lecture number 20 of group theory. So last time we have seen Sylow's theorem. First Sylow theorem, we have seen the proof by combinatorial argument, which was in fact even stronger version of Sylow's theorem that if p power alpha divides order of G, then G has a subgroup of p order p power alpha for any alpha, right? Not necessarily the highest power. So now we prove the Sylow's theorem, which is the actual statement of Sylow's theorem. That is also called Sylow's theorem, what we have proved last time. So this is again first Sylow theorem or Sylow's theorem. But in this one, we are going to see the proof by class equation. Okay. So let G be a finite group and P be a prime. Such that P power M divides order of G. P power M divides order of G. But P power M plus 1 does not divide order of G. Then this theorem guarantees the existence of a P0 subgroup. What is a P0 subgroup? It's a subgroup of order P power highest prime power. So then G has a subgroup of order P power n. That is, G has a P0 subgroup. Right. So this is also this is another proof of the Sylow's theorem, which we are going to see. The second proof. Right, and because this is by class equation, is very similar to the proof which we have seen. All those proofs by class equation, and also it is similar to the proof of Cauchy's theorem for abelian groups we have seen. So this proof is comparatively very easy, easier than the previous one. I mean, it depends on the personal choice. If you learn that first, you find you understand that you. I have seen students saying that the first one is easy. Some people are learning this one before the first one, so they say that this one is easy. So it depends on which proof you find it easier. But yeah, if it is asked that prove by class equation, then you have to prove this result. If it is asked for any just prove Sylow's theorem, state and prove Sylow's theorem, one can state this, one can prove that, and then as a corollary, if it has a subgroup of all alpha, p power alpha for all alpha, then of course it has subgroup of order p power m. Right, so that follows as a corollary of the previous one. But let us prove this. So we prove this result by induction on order of G. So first case, we consider base case, order of G equals to 1. Uh, the result is vacuously true. So the result is nothing to prove because there is no prime dividing. So the result is vacuously true. Okay, no need to consider another case, but let us consider one more base case. This is called base case, where we show, yes, order of G equals to 2 in this case. So in this case, G has a subgroup of, in this case, 2 power 1 divides order of G, but 2 power 2 does not divide order of G. So G has a subgroup of order 2 power 1. So G has a subgroup of order 2. G has, here G has a subgroup of order 2, which is itself right? So it is itself. So in that case, there is nothing to prove also here, because it is itself, itself is a subgroup of order 2. Okay, so the base case is done. Then what we have is induction hypothesis. This is yeah. What is induction hypothesis? We assume that result is true for all groups with order less than order of G. Suppose the result is true for all the groups with order strictly less than order of G. Same kind of argument what we have done previously. So it is very, very similar. Yeah, so this means what? If I have any group whose order is less than order of G, and for that group, if some power of prime divides, and then the next power does not divide, then it has a subgroup of that prime, highest prime order, highest prime power. So that we can use this whenever we have such a case. So now we come back to G. So these two base cases we have considered, order of G equals to 1 and 2. Induction hypothesis, we have assumed result is true for all those groups with order strictly less than order of G. That means if any subgroup has order strictly less than order of G, and for which such a prime power divides, then they have a subgroup of that order. So now let P be a prime such that P power M divides order of G, but P power M plus 1 does not divide order of G for some integer M. Here, okay, for some M. Okay, yeah, suppose for some M, some integer M, yeah. Now in this case we have two cases. So we have case 1. What is the case? H is a proper subgroup of G, which is a very easy case. H is a proper subgroup of G, and P power M divides order of H. Then we are happy. Yes, so that means there is a proper subgroup so that P power M divides order of that proper subgroup. આવું એક subgroup મળે ધારો કે this is the first case. So in this case, so clearly P power M plus 1 does not divide order of H. Why? Because G net divide not kartu. P power M plus 1 does not divide order of G, and H is subgroup of G, and H is a subgroup of G. And since H is proper, H is a proper subgroup, of G, order of H is, we can say that it is strictly less than order of G. Yeah, so we have a subgroup H, so that P power order of H is strictly less than order of G, P power M divides order of H, and P power M plus 1 does not divide order of H. કેમ કે G ના order ને divide નથી કરતું, subgroup ને ક્યાંથી divide કરે? Yeah, it is even smaller maybe, or equal. Yes, so what we have in this case, so by induction hypothesis, the result is true. So H, it has strictly less than this, so we have assumed the result is true for order strictly less than order of G, and for which this is there and this condition is satisfied. So then by induction hypothesis, H has a subgroup K of order P power M. But since K is subgroup of H, since K is a subgroup of H and H is subgroup of K, H is subgroup of G, and H is a subgroup of G. K is a subgroup of G. K is subgroup of H. H is subgroup of G. So K is subgroup of G. K is a subgroup of G, which is K. What is the order of K? Order of K is P power M. So that means K is the required P Sylow subgroup. This is what we wanted to prove. Then G has a subgroup of order P power M. So which is the required P Sylow subgroup of G. Right, insert one page. Okay. Yeah, so in this case we have very easy, right? H is a proper subgroup and P power M divides order of H. So there is a proper subgroup such that P power M divides order of H. This is the first case. What is the next case? P power M does not divide order of H for any proper subgroup. So P power M does not divide order of any proper subgroup. So that is the next case. In this case we are done easily. So next case is, yeah, case 2. P power M plus 1. So P power M does not divide order of any proper subgroup of G. So here H was a subgroup. H એવું subgroup exist કરે છે, proper subgroup, so that P power M divides order of H. This is there, and in that case we have found a subgroup of H because we can apply the theorem. But now P power M does not divide order of H for any proper subgroup H of G. So that is P power M does not divide order of H for any proper subgroup H of G. Right, in this case as I said, proof by class equation, so we introduce class equation. So recall the class equation of G. Class equation is very important because of that. Yes, many applications are there, class equation. So order of G is order of Z. Z is the center, plus summation where NA is not equals to G, because when NA equals to G, that party comes here. Yes, so this is order of G upon order of NA. Yeah, so now if NA is proper subgroup of this, okay, so if NA is not equals to G, we consider this case. So the proof is very similar to what we do. Right? We say that some prime divides this. So it is true for all this, the prime divides this sum, that divides this, so it divides the difference, so it divides Z. And then our story begins. Right? Okay. Yeah, so if NA is not equals to G, then that is if NA is a proper subgroup of G, then by our assumption, what is our assumption? By our assumption, we can assume that P power M does not divide. By our assumption in this case, આ કેસમાં શું લીધું છે? P power M does not divide order of any proper subgroup. So if NA is a proper subgroup of G, subgroup તો થાય. That is, we have seen. હવે એમાં question ના કરતા કે આ subgroup કેમ થાય. So that ship has sailed. Okay, so it is a proper subgroup. Then by our assumption in this case, we have P power M does not divide order of NA. but p power m, what we are given, p power m divides order of g. So therefore we can say that p divides order of g upon order of na. At least this much we can say. Why? Because here the powers of p dividing order of g is m. ન્યુમરેટરમાં p power m છે, denominatorમાં p power m નથી, and it is subgroup, so of course it is strictly less than m. Maximum it can be m minus 1, so they are not going to cancel out. ઉપર તો એક વધારે રહેશે, at least one power will remain, right? Here p power m does not divide order of na, so maximum કેટલા હશે? Maximum will be p power m minus 1, because it is subgroup, it is going to be less than that, so it is a divisor of order of g, so powers will be of course less than this. So at least if all powers will get cancelled, at least one power will remain. So I am saying p divides. I am not saying p power m. I am just saying p divides this. Numerator has p power m fixed. Denominator does not have p power m. It is less than, strictly less than, because it is proper subgroup we are considering. So whenever it is proper subgroup, we have assumed that p power m does not divide order of na for any proper subgroup. So na is proper. Yeah, so p will divide this. Okay, and so hence this is true for all such terms here. When na is not equals to g, that means when na is proper subgroup, it is true. So then p divides summation na is not equals to g, order of g upon order of na. Also p divides order of g. Also p divides order of g. In fact, p power m divides order of g, but we can assume p divides order of g. So where we are going with this, can you see? So by class equation, we can say that p divides order of g minus summation na is not equals to g, sum over this order of g upon order of na, right? And then this implies by class equation p divides order of z, because by class equation this is nothing but p divides this term, p divides this term, so p divides the difference. So I can take this on this side, so it becomes minus. So what will remain is order of z, right? કચરો બધો clear કરી દો એક જ minute. Yeah, so p divides order of z, so order of z is at least p, right? And by Cauchy's theorem, here we can apply Cauchy's theorem. યાદ આવી ગયું મને. By Cauchy's theorem, z has an element of order p. Cauchy's theorem, if a prime divides order of subgroup or order of group, then it has an element of that order. So z has an element of order p, let us say b. So that is b belongs to z, order of b equals to p. So now let us take subgroup generated by b, right? So subgroup generated by b will be e, b square, and up to b power p minus 1, because order is p, so b power p is identity, so it's a cyclic subgroup. So what is the order of b? So then order of b is also p. It is same as order of the element generator, so that is also p. So if you remember this kind of proof, when induction is applied on order of g, right? So we have said that we prove this result by induction on order of g. So what we do, we somehow use this induction hypothesis. So we come from order of g to something which is less than order of g. If we can find trivially, that is no problem. But if we cannot find it trivially, then we cook up something and go in. This is usually the case that we go in the quotient, right? So that is why quotient is important, because when you take g quotient some subgroup, then the order of that group is going to be strictly less than order of g. So now here we have found a group b, And what we do is now take G quotient B, but for that we need to be sure that B is normal. B will be normal because element B is in Z. Since B is in Z, B square is in Z because Z is subgroup. B cube and all these powers are in Z because Z is subgroup. So if the generator is in Z, then that means this whole group is in Z. That is subgroup. So since uh, check this, since B belongs to Z, this B is a subset of Z, right? Because generator, since Z is a subgroup, so generator जो आ भी जाए, B itself is in Z, so Z is subgroup, so B square is in Z, B into B into B, B cube is in Z, so all powers are in Z. That means the whole subgroup. If the generator of cyclic group is in some other group, then it itself is a subgroup. So B is a subset of the center. That means that is elements of B. Elements of B commutes with every element of G. Oh, not commutes with each element of, because all the elements of B are in Z, that means all the elements of B commute with all the elements of G. So hence B is normal. Normal thase pi. Check this, verify. Right? If you have doubt, just do the computation. So hence B is normal. Yeah. Okay. So B is normal. So we can talk about the quotient. So let consider the quotient group. Therefore, we can form the quotient group. G quotient and call it G dash. Right? We call it G dash, which is G quotient B. Okay, I did one page. Yeah. So what is order of G dash? Order of G dash is order of G quotient B, and we know this is order of G upon order of B, which is nothing but order of G upon P. Order of B is P, as we have seen here. Order of B is P, right? So let me mark this with some color if you want to refer. This is P, and so which is strictly less than order of G, right? So this is how we come from order of G to something which is lower than order of G. So this is how we use induction hypothesis. But now we have to verify whether statement holds true or not in this case. So the condition. What is the condition? So we know that since P power M divides order of G, but P power M plus 1 does not divide order of G. This is given in the statement. Sylow's theorem. This is exactly what we are proving. So what happens in G dash? G maximum power શું છે? P power M. P power M plus 1 does not divide order of G. Then what happens in G dash? It is reduced by 1 power of P. Right? It is exactly order of G upon order of P. So what we can say, since this is the case, we have what we have? We have P power M minus 1 divides order of G dash, because order of G dash is nothing but order of G upon order of P. But P power M does not divide order of G dash. Is it clear? G dash. Now we apply induction hypothesis on G dash. Order of G dash is strictly less than order of G. And what is the highest power of P dividing order of G dash? It is M minus 1, not M. Here in this case it is M minus 1. So we have find a subgroup of order P power M minus 1 and then go back to G. This is how the technique is. Very standard result. If you read the proof of all this theorem, you will find it very comfortable. If you find it difficult, that means you have not gone through the proof of Cauchy's theorem for abelian groups. You have not gone through the proof of this class equation, what we have seen in the general Cauchy theorem. And when we showed that group of order P power n, Zg is cyclic, every group of order P square is abelian. All this has similar arguments. So this result will be easy if you have gone through those proof. Right, so then by induction hypothesis, we can apply on G dash. Induction hypothesis. G dash has a subgroup say P dash of order, which order? Highest prime power for G dash is P power m minus 1 of order P power m minus 1. So G quotient G dash is nothing but G quotient P, G quotient B. Anu subgroup se we call it P dash. So now from P dash we go to P. So we take let P equals to, and finally let P equals to all those x in G. See, P dash is subgroup of G dash. What is G dash? G quotient B. So P dash કેવું હશે? Right? It is also of this form, quotient B હશે. So all those x in G such that xb, right? xb શેમાં આવે? આમાં આવે ને G quotient this xb. But we are going in P dash. So બધા G નહીં લેવાના. If I take all those, so બધા x નહીં લેવાના. If I take all those x, xb is in general an element of G quotient B. But I take those x such that xb is in P dash. This is the idea. Okay, let me define it. And then so xb is in P dash, right? P dash. So P is all those x in G such that xb is in P dash. And then we have to verify. This is I write in red. Then P is a subgroup of G. And P is isomorphic to P dash is isomorphic to P quotient B. This is the thing I ask you to verify. This much. Right? Two things, very simple thing. This is how it is defined. Take x and y, show that it is product. Take inverse, show that it is there. So what we have to do is we have to verify that P is a subgroup of G and P dash is isomorphic to P quotient B. Then order of P dash is same as order of P quotient B, which is equals to order of P upon order of B, but which is equals to order of P upon what is order of B? Order of B is P. This P is capital P. This is small p. Yeah, this implies what is order of P dash? P dash is a subgroup of order P power m minus 1. Done. P power m minus 1 equals to order of capital P upon P. So this implies order of capital P equals to P power m. So thus P is required. P Sylow subgroup of G. This is what we wanted to prove. Okay, so two simple exercises are remaining. Just verify this and quickly you can see once again the proof. So this proves, so we have proved another part of Sylow's theorem, right? Another proof of first Sylow theorem. This is the second proof what we are proving. What we have proved, sorry. And the third proof, as I said, includes 2-3 results. For that we need some concept what is called double coset, and that we are going to anyway consider. So some part of third proof we are going to see, but we are not going to see third proof as a whole for now. We are going to postpone it and see if the time remains. Otherwise you'll have to do as an exercise. And so next in the next lecture we see the concept of double cosets, and after that we can go to the second part of Sylow's theorem. So Sylow's second theorem, and then Sylow's third theorem, then some applications, very important examples. So that will end the unit. So this unit is very small. comparatively. The proofs are bigger, but the content is less than the first two units. Okay, so see you in the next lecture.